Yeah, hello, good evening everyone. Am I audible?
Yes. Good evening.
Good evening, sir.
Yeah, good evening. Yeah, okay, Chaitanya, I have read your questions or doubts. So some of them are already included in the PPT. So which were left, we will talk in the after in the end of this class.
Okay, sir. Thank you, sir.
Yeah. Okay, so let's start. So we were talking about radiation in the last chapter or last class. So what were three types of radiation we were talking about? Anyone can tell? Types of radiation like direct, diffuse and global. Yeah. Susrut Mane, yes. So these are like, this is a pictorial representation which is showing direct beam and diffuse radiation, and these are ground reflected radiation. So anything which is coming here, these are direct radiations, and after diffusing with anything like particles in the atmosphere or any object, these are diffuse radiation, and both like direct plus diffuse becomes global radiation. So this is just a pictorial representation for your understanding. So do you know how we measure this radiation, like direct radiation or beam radiation, direct beam or diffuse radiation? Do you know? Do you have any idea how we measure practically these types of radiation? This question is based on the measurement of this radiation. It says choose the correct regarding pyranometer and periheliometer. So these are the two devices which are being used to measure the direct radiation and diffuse radiation, or we can say global radiation. So these are the options. Just let me know if you know about this pyranometer or periheliometer. If you don't know, then just let me know via chat box. I'll tell you what are these devices are. Anyone like have any idea about these things? No. It's okay if you don't know, you can type no. It will save our time. No, okay, Chaitanya. So, like there are two devices, pyranometer and periheliometer. So first we will see what are these devices, then we will come to this question again. So these are the two devices. So as you don't know, so I'll tell you, this is pyranometer and this is periheliometer. So can you guess? There are two radiation, like global radiation and beam radiation or direct radiation, beam direct. So can you guess which one may be used for which radiation type? Just take a guess based on this structure. Just see this structure and this structure and take a guess. Periheliometer for what? Direct. Okay, so he is saying for direct we use periheliometer, and then for global we use pyranometer. Yeah, Vaishnavi, you are right. So Sas, you are also right. Direct perihelio. Chaitanya, you are right. Okay, so see what happens. This is a structure. It's like an hemisphere. So what happens here? Radiation can come from any direction, like this. So what kind of radiation will come from all direction? It will be a global radiation. And here only one directional ray can enter in this device. It's like this. Only one direction. So it will measure our beam radiation. So what is the mechanism behind these devices? So what happens? There is an, we can say, thermocouple here, also thermocouple plus PV cell. So the combination of thermocouple and PV cell measure the amount of radiation present in the atmosphere. So I just took these things to let you know what are the devices we use for radiation measurement. Any doubt here? No. Okay. Major questions, like it says, have you read about photoelectric effect as well as photovoltaic effect? So does anyone know the difference between photoelectric and photovoltaic effect? Yes, Chaitanya.
Sir, in photoelectric effect, we excite the electrons from metal into the atmosphere, sir. In photovoltaic, we just excite the electrons, but they'll be within the system itself.
Yes, absolutely right. So here what happens, the electrons comes into the atmosphere. More generally we can say it's vacuum. It comes in vacuum and it remains in material. So this is the basic difference between photoelectric and photovoltaic, and like based on the mechanism both are right. Sorry, both are same. In both the things what we are doing, we are having beam of light, or we can say sunlight, or we can say any radiation. It is causing electron or excitation of electron, or we can say removal of electron. So in this photoelectric effect, what happens? These electrons remains in the atmosphere, while in the photovoltaic effect, these electrons goes into the material itself. Okay. So I hope all of you got it. If you have any doubt here, you can ask.
Sir, can you please explain once how like photovoltaic effect exactly takes place when light falls on how current flows?
Okay, so that's the course is about. It's like, I'll tell you in like very short. So it's, see, we have this PN type semiconductor. It's like N type here and P type here. It's a PN junction semiconductor, and here we have depletion region, we can say. So what happens when light comes here on the surface of this solar cell? The charge carriers are generated. It's like, first step is steps. My camera is okay. So what happens? First, absorption of sunlight take place, and what it does, it create charge carriers. What are the charge carriers? Electron plus hole. And then third is, these are separated and collected. So in short, we can say, if light is coming on the surface of solar cell, what will happen here? This light will cause pair of charge carriers, and these charge carriers will be separated due to this like voltage, or we can say potential in PN junction. So these are separated due to this PN junction, and these are collected by the metal contact. So this is the complete photovoltaic effect. In more detail, you will understand, like we have, I think, have you gone through the lectures? Yes or no? In the lectures in this week, it just started about this photovoltaic only.
Yes, sir, I have gone through the lecture, but not clear, sir.
Okay. So now you have any doubt? Do you know? Do you understand?
Sir, here also, yes, sir. Sir, here also you have drawn that N type very small, narrow,
Yes. That I'll tell you.
and very broad.
That I'll tell you. I already have a slide in this PPT.
Yes, sir.
About this narrow thing and this broad thing, I'll tell you. Okay. So what I was talking about? Okay, it's done. Oh. So now let's come to the basic things, like what are the types of material based on the conductivity? It's conductor, semiconductor, and insulator. And which material is being used for this photovoltaic effect or solar cell? Write in the chat box. Do you think it is conductor, insulator, or semiconductor? Semiconductor. Yes, Vaishnavi. Chaitanya, you are also right. Semiconductor. So what is the difference between conductor, semiconductor and insulator? Semiconductor band gap. Okay, it's very short, but it's okay. So it is like based on the energy gap or band gap, we can distinguish semiconductor, conductor and insulator. Yes, yes, Vaishnavi, yeah, it's energy gap or band gap. So let's move further. Okay, conductor, complete conductor conducts partly semiconductor. Yes, Pawan Kalyan, yes. So based on the band gap, we will see these are like conductors. So what happens? We have valence band and conduction band. 0.5 to 1.5. Okay, okay. Yes, Chaitanya, you are giving us the values. So here also we can see valence band, conduction band. There is no band gap. Band gap is almost zero. It's complete zero. In case of a semiconductor, there is a little band gap, and in case of an insulator, there is a large band gap. So just tell me why there is no conductivity or no conductance in case of insulator due to this band gap. It means I am asking the definition of band gap, or what is the role of this band gap. Role of this band gap. Okay, I'll tell you. It's like electron will jump from valence band to conduction band. Energy more than the band. Yes. And if energy is more than the band gap is not available, then those will not conduct. So it's like conductor, there is no band gap, so it's always a conductor. In case of a semiconductor, it's like thermally activated conductor, we can say. So if we will increase the temperature, then the conductance will take place. But in case of insulator, what happens? It is not possible to give that much EV practically. Yes, Chaitanya, absolutely, you are correct. In case of insulator, there is no energy available to electron, or it is not enough energy available to electron to jump the band gap. So that's why insulator remains the insulator. Okay. So let's draw the band gap for a PN junction solar cell, or we can say PN junction device. So what do you think how it should look like? Okay, I'll draw, you just let me know the some things which I'll ask. So if this is P type, and here I'll draw N type. So if this is our valence band and this is our conduction band, and here it is valence band and conduct band. So where should I draw the Fermi level in case of P type and in case of N type, both? Where should I draw a Fermi level in case of P type and as well as in N type? It should be in middle or somewhere else, near to VB for P type and near to CB for N type. Yes, so we can say it's like, and here it is our Fermi level. at center for intrinsic. Okay, these are not intrinsic, these are like extrinsic p-type and n-type semiconductors. Yes, you are right, Deepsika. N-type below CB. Yes, Deepsika is also right. So now what will happen in a p-n junction device? What we do? We have p-type semiconductor, then we have n-type semiconductor. We just bring them together at atomic level. So there are different techniques. I am just telling you, we just bring them together. So it is not like we are having two different devices and we are just joining them. It's not like, it need to be at atomic level. So what will happen here? We will make a p-n junction type semiconductor band gap. So what should be the same? Fermi level should be the same. If we just draw Fermi level first, it is a Fermi level. Then for the n type, here will be our conductance band and here will be our valence band. And in case of p type, here will be our valence band and here will be our conductance band. So we are like making those devices at atomic level. So it will be like this. So this is our p type and this is our n type, and this complete is for p-n junction or p-n type band gap. So this is the way how we draw a p-n junction band gap. Same here, you can see in this picture, this is a p-n p type, this is n type, and this is the p-n junction band gap. Now there are two things. If light is coming at the junction side, this is our junction. So what will happen? Charge carriers will generate. Electron hole. These will be generated. And in the other case, if those charge carriers are coming down, so they will release some energy that can be in the form of heat as well as in light. So we can say like LED. LED are a p-n junction devices. So this is all about the p-n junction band gap. Now let's move further. If you have any doubt, you can ask.
Excuse me, sir.
Yes.
Sir, could you please explain like physically the reason behind why Fermi level will be close to valence band in p-type and close to conduction band in n-type, like physical reasons?
Yes. Okay. So just tell me the definition of Fermi level. It will be clear.
Sir, at absolute zero, it is the highest energy orbital that electron can occupy.
Okay. So it's like this is our p type. So it's like this will behave as a conductance band and this will behave as a conductance band. Why? It's like if our Fermi level is coming down, means we have more acceptor electrons, or sorry, atoms. We have more acceptor atoms, so they can accept an electron by having small energy. So it's like in a p type what happens? We have tetravalent impurity, right? So those are like having more number of holes. If those are number of holes are more, then their probability to accept an electron will be more or less. If there are so many more, yes. So in case of a p type, what will happen? There are so many atoms, so they can accept an electron much faster as compared to intrinsic semiconductor. So the band gap, real band gap is reduced, and this real band gap is nothing just a barrier between an electron to accept by an atom. Same goes, sorry I draw it, same goes with this n type. What happen in case of n type? We have pentavalent impurity, that's why we have large number of electrons. So it's like our electrons are filled here, we say na, above the, below the Fermi level or above the Fermi level. So below the Fermi level we have so many electrons, so these electrons can jump to the valence band easily. So here also this band gap is reduced. I hope it is clear now.
Sir, the second one I didn't understand, sir.
See, in case of a p, I'll draw here. In case of p type, you got it?
Yes, sir.
Okay, it's like I'm telling about you n type only. So if these are acceptor atoms, let's say, or sorry, I'm telling about n type, so it should be donor. So here we have so many donor atoms. So what will happen? The density of donor atoms is more. So they are having, it's like below the Fermi level there are so many atoms which can donate an electron. So due to this abundance availability of these donor atoms, what will happen? Our Fermi level will shift up because so many energy levels are filled with donor atoms, and that's why these donor atoms can donate an electron to conduction band. If we will compare it, we can say conductance band, valence band, here also conductance band and valence band. So if like
Sir, so it is because of population, sir, like more number of
Yes,
population of donor atoms are there.
yes, so we also see it in another way. We say that
Yes, sir, now I understood, sir.
yes, okay. Okay, so now let's come to the next point, which is about the temperature and conductivity. So what is the impact of temperature on the conductivity of metal and semiconductor? What do you think? The conductivity of metal increases or decreases with temperature, or the conductivity of same way like conductivity of semiconductor decreases or increases with temperature? Just think, you just think in a two way, what are the regions for the conductivity in case of metal, and same thing with the semiconductor. Think, just let me know it's increases with temperature in case of metal or decreases. Metals conductivity decreases with T temperature, okay, and semiconductor conductivity increases. Yes, absolutely right. I'll be happy if you can give me reason as well. Just think about it, it is very easy. So I'll show you the graph. It is the conductivity, or we can say resistance. So resistance of conductor increases with temperature, so conductivity decreases. In case of semiconductor, this resistance decreases with temperature, so the conductivity increases. So what are the reasons why semiconductor and conductor are behaving differently or in opposite direction? collision among electrons. Yes, absolutely right. Yes, Mamta, you are right. So in case of a conductor, we have large number of electrons. We say sea of electrons, and due to this sea of electrons, what happens? The collision takes place, and due to this collision, resistance offered to the electron is more, and that's why the conductivity is less. Yes, and what about the conductor then? Sorry, what about the semiconductor then? Why it increases in case of semiconductor? I I told you like in the starting only. When I was discussing about the band gap theory, then I told you what can be the reason. You can guess it from that. Conductivity, thermal excitation increases with temperature. Yes, you are right. So what is this thermal excitation? In case of like in terms of band gap, you can tell me what is this thermal excitation? Transfer of Mamta and Chaitanya. Okay. Transfer of electrons is easy from valence band to give rise to increase in conductivity in semiconductor. Yes, absolutely correct. What happens? We just for the conductivity, what is the minimum requirement? Just jump this. We need to jump from this valence band to conductance band. So this is the minimum requirement. If an electron is having some kind of energy, and if we are giving some thermal excitation or we are giving some thermal energy, then the energy with this electron will be more, so it can jump this barrier easily. Yes, you both are correct. Okay, so next question here is very simple for you. I think you most of you know it already. So it is just like what is the difference between drift and diffusion? What is drift and what is diffusion? Both are related to the movement of electron or movement of charge carriers, but there are different causes between behind those. Like drift is caused by different reason and diffusion is caused by different reason. So what is the reason then? Within junction transport is drift, and in quasi-neutral region transport is by diffusion. Drift is due to applied electric field. Diffusion need not require any external factor. Mamta, you are right, but it requires some external factor, and that is the difference between the concentration. So we can say concentration gradient. So in case of drift, there is electric field, and in case of diffusion, it is concentration gradient. Yes, Chaitanya.
Sir, during the lecture, I got one doubt, sir, regarding this. Sir, my doubt is like when we make like a PN junction diode, like during the process of making itself, do we get this inbuilt potential difference at the junction? Is it like that or we have to apply externally, sir?
No, we see what happens when we have P type and N type, then we diffuse both them. So there is a diffusion of charge carriers, and due to this transfer of charge carriers, the potential is already built up already, means in itself. So we don't need to apply any potential.
Okay, sir. Sir, and this potential which got built up at the junction, it will remain like that only, sir. Like forever, like that.
Yes, it will remain like that. It decreases or increases based on the external applied potential. But if we are not applying any kind of potential, then it will remain same. Your question is about knee
Okay, sir,
voltage.
based on the
Yes, your question is about
yes, sir.
knee
Yes, sir.
voltage, and it is related to that only. So the potential which is built up, see, I'll tell you. If we have P type and type, so what will happen? Here we have hole, and this hole will move this side due to concentration gradient, and here we have electrons, and these electrons will move here. So when electrons are moving, so what happens? The positive charge will generate here and negative charge will generate here. So due to this, a potential difference will be created here, and this is permanent. That's why the IV characteristics of a semiconductor is like this. After a particular point, this increase in current is more with voltage, and this is known as knee voltage, and this is the potential you were asking in your question. So this is the potential and this is the knee voltage, and this knee voltage is nothing but it's like, if we are having, just see here, if we are just applying an potential here, so we are having V external. So whenever V external will be more than this V potential, this range we will get, and whenever this V external will be less than this V, so this is the range we will get. So after a particular point, after this barrier, so this is a barrier for us. In case of a forward bias, it is a barrier, because what happens, we are having positive charge here, but we have an opposite. See, this is an electric field direction is here, and we are applying, it's like negative here, positive. Our electric field is here. So these are the opposite direction. It's like one E external is here and E internal is here. So total effective should be E external minus E internal. So this case will be in this range. I hope you got it. So this potential which is already being created when we process this PN junction diode, it is the potential. I just refer your question. What is the difference between knee point and junction potential? Yes. So this is the junction potential, nothing else. It is a junction potential in a PN junction diode. And about this knee voltage we say in terms of external voltage. So whenever this external voltage is equal to the potential or junction potential, then we say this is the knee voltage of the semiconductor.
Sir, then it should be zero, like from that point onwards it is increasing, right?
Which I'll see. This is region 2, this is region 1. Then let me know which region you are talking about.
Sir, I am talking about at that point, sir. At that knee voltage point, it is starting to rise, right?
Yeah. Abrupt change, yes.
Yes, sir. So why it is coming exactly, sir, at that point itself? It is because knee voltage and junction potential both are numerically same, or
See, it's like this is our voltage. Let me create a, see, if this is our semiconductor P and N, and here we have V, the direction of this V is like positive, 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 negative, 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 and here we have external V external. Now just compare this with something else. I'll tell you. So if we have a battery like positive 5 volt and we have other battery it's like, I don't know have you solved this kind of question or not. 2 volt and this is some R. So how will you calculate I here? Because these are in opposite direction. Same thing here. See, the current from this battery will flow this direction, the current from this battery will flow in this direction. So it should be like minus 1 from another. So same case is here. If we are having external like this external is causing positive charge here, negative charge here, and this is our V, this is our I. I just started increasing this voltage. What will happen? Let's say V external, and here we write V external minus V. V is this potential. So let's say V external is 0, then V external minus V is, I'll put it in 2 volt. Let's say 2 volt. I am just taking it 2 volt. It is not 2 volt, but I am just taking it 2 volt. So what will happen? Here it is 2 volt negative. I'll just apply 1 volt. It will be minus 1 volt. I'll apply 2 volt. It will be 0. So I'll apply 3 volt. It will be 1. So in this case, after overcoming this barrier, the charge carrier will start flowing. See, a charge carrier is here an electron, and this is our positive to negative electric field. So where this electron should go? Positive to negative. And due to this electric field, this electron should go in opposite direction. It will go in here and it will go here. This is F1, this is F2. Let's say there are two different forces, F1 and F2. So when when this electron will move, if F1 is greater than F2, F1 is equals to F2. What will happen if F1 equals to F2? F I am taking as a force. No, you are not getting right.
Sir, I got till like this point, sir. Like initially, when the applied voltage, external voltage is less, so the junction voltage itself is more. So the current flowing through the circuit will be because of the PN junction potential. So that will be very less. But as soon as you increase the voltage, external voltage, the current will increase slightly only up to the new voltage point. Afterwards, what will happen? The external voltage will completely dominate, and then the current will rise steeply.
Yes, and it's like it is increasing steeply. Why? Because this V is just 0.6 volt, and our parameters, like our characteristics, goes like it's about like 5 volt. So this 1.6 will be here only. So we are increasing like this. Sorry, here 0.6. So if we are having more potential applied to the PN junction diode, so this increase in current or flow of electron will be more. In an analogy, you can understand it's like here, if F1 there is a ball and F1 is applied in this direction and F2 is applied in this direction. And let's say this is applying 2 Newton force and this is applying 1 Newton force. I'll take different scenario, F1, F2, nothing like this. So F1, F2. Now just tell me if F1 0 and F2 is 2 Newton, then what will happen? This ball will go in this direction. And if this is 1 and this is 1, then what will happen? This will remain.
So it won't move.
It won't move. Then tell me, if F1 increases to 10 Newton and it is remain 1 Newton, then what will happen? So this will go in this direction at faster rate. So this is the
Yes, sir.
Characteristic, same thing. This is the, like, if this case, or we can say if our external applied voltage is comparable with the knee voltage or a potential PN junction potential, then the current flow will be very low. But if this potential, external potential, is much more than the knee voltage or PN junction potential, then the change in current will be more, or abrupt change will take place. I think now you got it. If you haven't got it, then tell
Yes,
me.
sir. Yes, sir.
Okay. Okay, we were talking about this drift and diffusion, and I think, like, who said, Chaitanya and Mamta? Yes. So you already said it. What is drift and what is diffusion? So it's like we have potential difference here. Can I clear this? Yes. So here we have potential difference, like positive, negative, and here we have concentration difference, high concentration and low concentration. So this will be a flow and this will be a flow. So this is due to diffusion here, and this is due to drift. Okay, let's move to the next part. So based on the band gap theory, you just need to identify some points in this figure. Please identify. So identify this A, B, C and D. A and B are the type of semiconductor, and C and D are like level, acceptor or donor. Just tell me, what is this A? A is P type, okay. P type from Deepsika, okay. B is N type from Deepsika only. What about C and D? C and D are Fermi level. We also know those Fermi levels with some other name. I just told you acceptor and donor level. So which one is which? Like, which one is acceptor and which one is donor? Which one is acceptor level? D is donor. D is donor and C is acceptor. Srustmane, B Madhumita. Okay, let's see. Correct answer are A is P type semiconductor. Yes, you are right. B is N type semiconductor. Yes, you are right. C is acceptor level. Yes, absolutely right. Madhumita and Mamta and Srustmane. And D is donor level. Yes, absolutely correct. Now let's come to the free electron theory. Just let me know the reason why this curve is parabolic. Just first I'll tell you, this is an KE. K means our, we can say, wave number, or we also denote it with PH cross K. So it is wave number, or we can say momentum energy space. So here you can say it is momentum and it is our energy. So why it is parabolic? And this is for an electron. isolated atom. This is for an atom having a free electron. Just think about it. E equals to h square to k square h square, distribution of energy. Yes, distribution of energy. Chaitanya, you are right. Just in the simplest term, we can say what, see, the movement of electron is related to what? Its velocity. Yes or no? Yes. And this is about like movement of electron only. So we have momentum equals to mv and we have energy equals to half mv square. In a crude way, we can say this momentum is related to, directly related to with v, while energy is having an v square. So if we will just put v square in place of, sorry, if we will square v in terms of p, then we will get this parabola. Yes, Chaitanya, you are right. And Mamta, you are saying distribution of energy. It's about energy only. It's distribution of energy having different k value. So here I just want to tell you one thing. So for a single atom, we go with parabolic, but when we have different atoms in a lattice, so we have this kind of structure. And then those structures give rise to our conductance band and valence band. I am having a question based on this, so I just had this, I am just having this figure to let you know. Okay, so this is the question. Identify the type of materials 1, 2 and 3. 1, 2 and 3. You just need to identify the type of material. We just studied the type of material. It's semiconductor, insulator and metal. So, conductor, semiconductor and insulator. One is insulator. Deepshika, yes. Second is semiconductor. Third is metal. Yes. Insulator, semiconductor, metal. Yes, Mamta, you are also correct. Deepshika, you are also right. So here you can see this is conductance band and this is valence band. If I draw a line here at 0 point, so this is nothing like, this is our valence band, valence band, valence band, and this is our conductance band, conductance band. So here this is the band gap and no band gap. So that's why one is insulator, 2 is semiconductor and 3 is conductor. Okay, let's move next. Now let's come to a type of semiconductor based on the band gap. So we have direct band gap semiconductor and indirect band gap semiconductor. So can you just let me know what are these direct band semiconductor and indirect band semiconductor? valence band, conductance
Sir,
band.
momentum should be aligned. Momentum should be aligned.
Momentum should be aligned. Okay, not aligned in indirect. Mamta is saying valence band, conductance band aligned in direct and not aligned in indirect. Okay, so silicon is direct or indirect?
Indirect, sir.
Indirect. Indirect. So what are the benefits of direct band gap?
Sir, they will emit photons, sir, and no phonons.
Okay,
And indirect, they'll first emit phonon and later they'll emit photon.
phonon vibrations are involved in indirect. Okay, so what do you think the material of a LED is? Light emitting diode.
Sir, gallium arsenide.
Yes, it's direct. Okay, so this is a pictorial representation. You can see in this like this is our direct band gap semiconductor. This is indirect band gap semiconductor. So here the movement of electrons should be like this, and here it should be like this. Okay, next question, it says in an indirect band gap semiconductor, an electronic transition between the conduction and valence band results in. These are the options. I am talking about indirect band gap semiconductor. D. 4. D. Deepsika, Chaitanya and Mamta. Yes. All of you are correct. It's D. Change in both momentum and energy. Yes. It's D. Yes, Chaitanya, you can speak or you can write.
Sir, yes, sir, I have a doubt, sir. Like in lecture, it is mentioned that silicon and germanium gallium arsenide comes under direct. Sir, this is purely experimental result, right? Based on the spectrum which you showed like earlier one. Hello.
Are you asking reason for the direct band gap or what?
Like why silicon became like in silicon, why the that misalignment of momentum came, sir? Like it is a its characteristic feature, right?
Yes. Yes.
So how we came to know that, sir? By experiments only, right?
By experiments only.
Without the
Yes,
yes, sir.
even this like this K versus E is an like abstract diagram. It is not like we can see it in the semiconductor.
Yes, sir.
Yeah.
Sir, and also in previous questions, sir, so many curves are there in that spectrum, sir. Like, how did you identify that that is the valency and that is the conduction band, sir? I have seen that you have taken like below the zero, it is valency
Yes.
band.
Yes, yes.
Is it every time we have to do like that only, sir?
Yes, yes. Actually, all those figures, it's like only. And one more thing, these are like V versus K versus E diagrams. So what happens? We generally try to solve this for 1D, 0D, but it is very complex for 3D structure. And in real life, we have 3D structures. All means all the structures are 3D lattice. So that's why there are large number of curves you can see in the figure. And for this band gap, like conductance band and valence band, we take 0 as a reference point. Okay. So next question says, which of the following is or are true for extrinsic semiconductor? It's very simple. So it is asking for a relation between N and P means number of electrons and number of holes, or we can say concentration of hole and electron with intrinsic carrier concentration. So these are the options. Yes, Chaitanya. Ni square equals to Np. C. Yes, all of you are right. B. Madhumita, Mamta, Deepsika and Chaitanya. So this is known as which law? Law of mass action. Yes. It's C, right. Next question. It is an okay. So it is a numerical based on the same thing. You just need to solve it. So here we have hole concentration 1.25 into 10 to 18. Then we have intrinsic concentration. You just need to tell me the electron concentration. Do it and solve it right now and tell me. A, B, C or D? A. Kartik A. B. Madhumita A. Deepshika is saying A. So we have 1, 2, 3, 4. Susrost Mane is also A. It's very simple. Yeah, it's mass action law and solution is here. Np equals to Ni square. We will just put the values here. It's like 1.25. It's P and then we have Ni here and we just solve it. We will get 5 into 10 to the 6. A is the correct answer. Let's move to the next question, which says, so this is based on this. Yes. So this is based on the curve I told you about, K versus E graphs. So it is asking the allowed range of K for the first Brillouin zone. These are the options. B. Chaitanya, Mamta, Susrust and Deepsika. All are right. It is B. This one. Okay. For the second Brillouin zone, so we will consider this thing or we will consider this thing. Option A or option B? A. Sorry, I got confused with A, B. Let's see 1 and 2. Will it be 1 or 2? 1. Okay, just check it again. If you are right or wrong, this is your homework. Second Brillouin zone should be from minus 2 pi a to 2 pi a, or it should be a discrete value from minus 2 pi a to minus pi a and pi a to 2 pi a. Yes, here B is the correct answer. Deepsika is saying 2 and others are saying 1. So this is your homework. Okay. So this is the next question, which says the Bragg condition for one dimensional solid with lattice constant A is, and these are the options. It is a direct question. You can just tell me by seeing the options. A, B, C or D? A. Chaitanya, A. Mamta is also saying A. No one is with C, D. Okay, A is the correct answer, right? Sanjeev, Siddhul, yes, it is A. Next question, it says momentum and wave number is related as. Momentum and wave number, the same thing I was talking about. This is the option. Momentum and wave number. Chaitanya D, Deepsikha D, Sanjeev D, 1, 2, 3 D, 4 D, only 4. Okay. Yes, it is D. Amit Kumar is also saying D. Okay. Okay, now let's come to the very important thing, that is the IV characteristics of a solar cell. I'm just asking one question. You have seen the characteristic of a solar cell like this, V and I, and it is like this. And you have seen the characteristics of semiconductor, that is like this, V and I. Now tell me why it is like that. It's like solar cell, it is semiconductor, but solar cell is a semiconductor. Then how this IV curve is different than the semiconductor IV? Can you obtain these characteristics from this? Yes, no. So have you thought about this question before? Why the IV characteristics of solar cell is like this, not exactly same as semiconductor, if solar cell is a semiconductor device? In solar cell there is no external circuit for flow of current, therefore current decreases with increase in voltage. There is no external circuit for flow of current, therefore current decreases with increase in voltage. But how can you control this voltage? See, this IV characteristics we only get it how? If we have a solar cell and it is illuminated with the sunlight and we are having a load and we change the resistance of the load, then we got the solar cell IV characteristics. So we can't say there is no external circuit, load is there. The graph is at room temperature, both are at room temperature. It is also at room temperature and it is also at room temperature. Just try, think about a solar cell. Therefore, current decrease with increase in voltage. Mamta, I just want to ask one thing. How voltage is being controlled if there is no external circuit? See, if there is no external circuit, that is known as open circuit, and current remains zero and voltage remains maximum. That is the condition you are talking about. The graph is at room temperature. Chaitanya, do you have any idea? Or anyone else? Deepsika is saying solar cell have some open circuit voltage due to photocurrents which get decreased with external voltage. Solar cell have some open circuit voltage due to photocurrents which get decreased with external voltage. You are making a big mistake here. You are saying external voltage. Then why we are using a solar cell if we are applying an external voltage? The IV curve given here for solar cell is from an independent solar cell without an external voltage. Anyone want to try? You can just build on this. Solar cell. Okay, so let me tell you. No responses. Okay. See, this is a semiconductor, and we are applying an external power supply here. Since the electrons are more free, so the current will be high once we connect it. Okay. Initially, current sorting is there in solar cell. Sorting or shorting, I'm not getting it. Like, are you about ISC or short circuit current? Binning. Okay, I just need to understand what Karthik is saying. He is saying since the electrons are more free, so the current will be high once we connect it initially. See, Karthik, you just need to understand one thing. Here x-axis is not time. So how you can say initially and on later stage? If it is a curve between I versus time, then we can say it is like having high current initially then decreases. But it is not the same case with solar cell. Pulkit, I am not getting what you are saying about this current sorting is there in solar cell. You should have done the last lecture. Okay, it's okay. So this is the external power supply. And the direction of current is here, it's like. So here we are getting IV characteristics. In case of a solar cell, what will happen? We are having we can represent a solar cell like this. This is a solar cell and this is the direction of current. And here we apply load. Connection lost. Hello? Am I audible?
Yes, sir.
Okay, screen is visible, right? I lost the connection for some time. Okay. So here, just see the direction of current. Here, direction of current is going away from the external source. Here, this current is coming toward the load or external load. So here, what will happen? We already have a current. Then this curve will shift down. It will be like this. This is our current voltage. So we already have a current source in a solar cell. So this will shift our IV curve. So it's like negative current, negative I. So this is nothing, just a reflection of this. So for the simplicity purpose, what we do, we just change the term. The incoming current is negative, but for the simplicity, we say it's a positive current, we are getting it. And we just reverse the curve and we get this solar cell curve. It is nothing, just a curve of a or IV characteristics of a solar cell. Any question here? No. This is the IV characteristics of solar cell. There are many tabs like external current source. There is no external current source. Solar cell is a current source already. Yes, Pulkit? Deepsika?
So can you explain it again?
Yes. Just see the direction of current. We are giving it to solar cell here. And here we are getting from the solar cell. So what happens if we already there is a current, then what we will see, if any current we are receiving, we say it is negative. If current we are giving to a device, we will say positive. So we are getting a current, then our curve will shift down. And for the simplicity purpose, what we will do, we will just take the current coming towards the external source as positive current. And we get this IV characteristics. It is nothing like difficult to understand. It is just one thing, the direction of current. In case of a semiconductor, we need to apply current. That's why we need to apply external source. That's why the current is increasing as much we are giving to the diode. But in case of a solar cell, there is current already. We are receiving that current. So that current is negative in terms of direction of current. So this is nothing like, just we are shifting this curve to the downside, and this is the shifted curve. And for the simplicity, we just like reflect it in with respect to x-axis, or we take I as positive. Now there are many terms which are handy for a solar cell to understand. First I will draw a circuit, then I will tell you with respect to IV characteristics. See, I told you this is a current source and this is a diode, and this complete is, these are terminal A and B, and this is our solar cell in terms of circuit or electronic circuit. So just tell me, if this is the I current coming from this and this is the V. First thing I'll ask you, if there is no connection here between A and B, what should be the current flowing between A and B? Or like conversely we can say, if the resistance between, yes, resistance between A and B is infinite, then current will, then current will be 0. And if current will be 0, then what should be the voltage there? Highest, yes. So where this point is? Here. Yes, that is known as VOC, means open circuit voltage. That is the maximum voltage of a solar cell. Now let's consider we are having a dynamic resistance R and we are changing this resistance. So what we are doing, we are going from infinite resistance R equals to infinite, R equals to 0, we are going in this direction. We are changing our resistance. So this is a particular position where R is something R naught, when this power, or we can say V into I, is maximum. So this is the point where we want our solar cell to work on, and this is known as maximum power point. So have you like studied or have you seen something MPPT, PWM? So have you seen these terms anywhere? MPPT, maximum power point tracker. No. Okay. So inverter, yes, it is not inverter, it is just thing before the inverter. It's like we have solar panel, then we have inverter. So between an inverter and like this solar cell or solar module, we have a device that track this point, this Pmax, because what we want maximum power to be extracted from a solar panel, and that maximum power can be extracted at a particular point, and that particular point can be traced using dynamic resistance, and this dynamic resistance things we can do with a device. So using this device, what we do, we just track this maximum power point and we obtain the maximum power. Now if this R dynamic resistance we are decreasing further and we are reached at a particular point where this R equals to, or resistance is equals to 0, then what will happen there? If this is short circuited, A and B are short circuited, then what will happen? What will be the current flowing through the A and B? Highest. Yes, ISC. ISC is the short circuit current. Current flowing when our condition is short circuited. So this is the point. Here current is maximum and voltage across zero resistance is 0, because V equals to IR. If I is maximum but R is 0, then it will be 0. Yes, Deepsika, voltage will be 0. So this is our ISC. So these are the three things like VOC, ISC and Pmax. These are the three parameters which are used to see the condition of a solar cell, if it is working fine or not. Here other thing comes like fill factor. fill factor is, it is defined as P max divided by ISC into VOC. It is the fill factor. So more the power, fill factor will be more. And efficiency is defined as P, that is extracting at maximum power point, divided by how much insolation we are getting into what is the area of solar cell. So this will be in watt, this will be in watt. We will get efficiency. Any confusion here? What FF signifies possibly? Yes. FF is telling about this power point or this point. Is it like, it is telling about the condition of a solar cell. If it is degraded, if it is having any kind of fault. See, there are two conditions. Let's see, our VOC and ISC remain same, but curve is like this. Our Pmax is here. VOC, ISC are same, but Pmax has been reduced. So to know how much it has been reduced, we are not going to see the Pmax value absolutely. We will just see a particular index, that is fill factor. Fill factor 1 is, it's like it is completely a rectangle or square, but that is not possible. But in case of, like, if there is some kind of defects and degradation, this Pmax goes down. And to know the health of a solar cell, we can't talk about the absolute value of Pmax. That's why we use this fill factor. Deepsika, I think I have cleared this, but if you still have any doubt, you can ask. Okay. Okay, so I'm having a small question. It says a small concentration of minority carriers is injected to a homogeneous semiconductor crystal at one point. The electric field is given 25 volt per centimeter, and the distance, the minority charge are moving at a distance of 2 centimeter in 40 microsecond. So you need to calculate the mobility. And these are the options. It is very simple. If you don't know the formula, let me know. Anyone write here the formula of mobility? Mu equals to E by Vd. E by Vd. And so first calculate this Vd, drift velocity. What is velocity? Velocity is distance upon time. Sorry. Distance upon time. And this is given distance 2 centimeter divided by 40 microsecond. So this is Vd. Then calculate. Chaitanya, you have calculated it. Okay. He is saying 2000. Someone else, are you trying it? C. Vinod Kumar saying C. So if you haven't calculated or if you are not willing to, you can just look on your screen. So it is given there, mu equals to Vd upon E. Vd we can calculate using the distance given and the time given, and E is already given here. So by using this we will calculate, then we will find out it is 2 into 10 to the power 23 or 2000 centimeter square per volt second. C is the correct answer. Next question, it says determine the wavelength. So I am talking about LED here. So determine the wavelength of light emitted from LED, which is made up of a semiconductor with a forbidden energy gap. It's 2.3, we can say band gap, 2.3 electron volt. And these are the options. So here it is all about LED. So you just need to calculate the wavelength of the light coming from an LED. E equals to Hc by wavelength, Hc by lambda. Yes. Yes, Mamta, you have written the formula right. E equals to Hc by lambda. What you need to calculate? Lambda. A. Deepsika saying A. Chaitanya is also A. Susrust Mane A. So have you calculated it like this? 6.6 into 10 quart minus 34 into 3 into 10 square 8 divided by 2.3 into 1.6 into 10 cube minus 19, or you have used approximation. Okay, yes, so like we also have an approximation. It's like this: 21242 divided by 2.3. Sir, I am unable to solve one assignment problem. Can we discuss it? Which assignment? Yes, so Suraj is 1240. Chaitanya. Okay, Chaitanya, you just let me know. I can discuss in the next class. Actually, I am not having energy much today. Yes, I'll discuss definitely. Assignment 1, okay. Because 2.3 electron volt is almost of visible region, we can imagine also. Yes, that is like intelligent guess. So 540, yes. Next question, it says the forward current in a silicon diode is 12 milliampere at 27 degrees Celsius. If reverse saturation current is 0.24 nanoampere, what is the forward bias voltage? These are the options. Someone please write the formula which is applicable here. Chaitanya, just let me know the question number. I'll solve it definitely. Does anyone know the formula here? Yes, no. If you don't know, then I can give it. Sir, I'm not remembering the number, but options will be like A by 2, A by root. Okay, okay, Chaitanya, I'll solve it in the next class. I'll look into it. What is the question and all. Mamta, J equals to, let me write your doubt. A upon 2, A upon root 2. Okay, so just solve it, this question. Mamta have already given. So it is given in the J form or J term. You can write in the I term as well. It is nothing, just current density and current. So I equals to I naught, or for the approximation you can remove this one. So what we have? We have this forward current, we have this reverse saturation current, and we have all these things. We just need to calculate this V. N is already given in the question. I think you missed it. It is 2. Someone please let me know the answer. I have the solution. If you are not solving, let me know, I can solve it. Particle in a finite potential box between the wave function approximation of schedules what will the wave function of. Okay, Chaitanya, I'll solve it definitely. Don't worry. So Chaitanya, what is the issue with this question? You don't know the formula, or you just applied the formula, or you are not getting the right answer? Have you tried it right, or you haven't tried, or you don't know the formula which need to apply there, and what is the integration and all? Yes, sir, I don't know the formula. Okay. Okay, give me the answer for this question. No one is solving, right? Okay. So this is given 15 milliampere. This is the forward current. So I is 15 milliampere. Then we have I naught, that is 0.24 nanoampere. and just okay, I got it. You might be having issue in solving all these Q upon NKT. So just for an approximation at room temperature, KT by Q is always 0.0258, or we can say 0.026 volt. So it's 26 millivolt. KT by Q. Exponential solving will take time, sir. Please show the answer. Okay, Deepsika. So I just told you here it is nothing like that. We can use the short tricks. So KT by Q is 26 millivolt, and by putting this here and by solving we will get its V equals to 0.93 volt. So C is the answer here. C. So next question, it says the total current density due to drift current and hold will be. Give me the answer in 1 second. This is not a question, this is just to identify the formula. The total current density A. Yes, Deepsika, because 2 can't be there, without electron it is not right, and 2 here can't be there. Okay, A. Okay, Chaitanya, Deepsika, you are right, it's A. The photocurrent equation is given as, just identify the formula. A, B, really B? I am having doubt. Chaitanya saying B, D. Okay, because 2 can't be here, 3 can't be here, 2 can't be here. So this is the right answer. It's D. Yes, last thing which you are asking about me, N side is thinner than P side. Why? There are 2 regions, one and 2. Just guess based on this figure. What might be the possible, so that photons will receive the junction easily? Yes, photons as well as electron need to go to the collector. Collector means our metallic contact, and they are having some kind of diffusion length, so they will die out, they will recombine before reaching to the metal contact. If let's say if they are generated here, let's say this is P and this is N, just 50-50, and if any charge carrier is generating here, so before going to this metal contact they will die out. First thing. Second thing, the light will not reach there as much it will reach here, because it will be absorbed by the material. Second thing. Third thing is that we are having charge carriers, it's like here, charge carriers from the width, from the this zone depletion region, plus the diffusion length of hole and electron. So we are having this kind of structure. And also you have seen one thing more, if N is less and P is more, then the junction will be more towards this P side. So this junction will be more deeper in the P side, and if it will be more deeper in the P side, then the charge carrier will be more, or generation of charge carrier will be more. And due to this thin N-type semiconductor or N-type material, our charge carrier generated here will reach to this metal. So that's why we have N-type is thinner as compared to P-type, P side. Okay, let me revisit your questions you asked in the starting. You said, my doubt, what is the difference between density of a state and effective density of a states? Okay, so like it's like, let me, DOS and effective DOS. If we have so many density of states, means distribution of energy states. So total energy states distribution is known as density of states, and if effective we are saying, then we are integrating some over some energy like dE, we are integrating over this, and we say effective because if we integrate it, it's like this, somewhere it is Fermi level, and these density of these states are fully filled and these are empty. What will happen if we take some dE here and we integrate over this thing, then we can get the number of electrons. So that's why we have effective and DOS. It is nothing different concept, it is the same thing, but out of total energy of states we are integrating over some state. Second thing is that what is the difference between knee point and junction potential? I told you, if we have a PN junction, this voltage which is built in this PN junction, that is known as junction potential, and if we are applying the external voltage, when this external VT will be equals to V, that is known as knee voltage. Please explain why P should be narrower, highly doped, and N should be wider. It's like reverse question. We have narrower N side and like wider P side. So I told you what are the reasons behind it. Okay, so it's already 7:53. Position of junction, please explain again, sir. Position of junction, I am saying, see, if it is like this, not this, let me draw here, and if it is like this, see, this is the junction, and we are having some other thing, we say quasi these things. So this junction is going some in N type, some in P type, so it is equally, but if N type is less than P type, so this junction will more in the P side as compared to N side. This is the position of junction. And second thing, position of junction near the surface will be more useful because it can receive more number of photons. That's why it can create more number of charge carriers. Yes, more number of charge carriers, and those charge carriers can be captured or can be separated by the metal contact. So this is the course is all about. In the upcoming lectures you will understand all these things. I think next week you will understand this solar cell absolutely, because coming week will be having these things in detail. Okay, So this lecture will be available on the YouTube as well. This is the like QR code of the YouTube channel, and even I can paste here as well. Wait. You can ask doubt on YouTube as well, and I will solve your doubt there. Okay, thanks for joining. If you have any question, you can just I can give you my email as well. So this is my email ID. You can ask me question there. You can ask question on the discussion forum. You can ask in the YouTube channels. K space, Chaitanya, I told you like K and energy space, it's an like energy versus we have wave number, or we have like potential energy. It's an abstract concept. Will the final exam objective or subjective? It will be objective only, like your assignments. I have given you my email ID. I have given you YouTube channel link. If you have still doubt, you can ask there. I will like clear all your doubts in the next class. Okay, thanks everyone. I'm just closing this class.